everyone. So now we're gonna start the subtrack language entity and NLP for African languages. Uh, this presentation examines active learning as a principled framework for building efficient, cost-aware NLP systems in low resource settings, with a particular emphasis on African languages. So please welcome with me Bonaventure.
Um, we are not many, so I'll.
For the broadcast, does it come from here? No, no, this one. It's for the broadcasts, that's why.
Okay, okay. Okay. So I was saying that I'm going to be talking with you through the whole concept of active learning, and like how we can use it to build more efficient African language technologies. So I'm not sure how many of you know about active learning. You probably just know much about like how to pre-train a large language model on a vast amount of corpus. A vast corpora. But is actually active learning is actually an interesting paradigm because it allows you to do what semi-supervised or self-supervised learning methods are doing, but by reducing the amount of like compute resources, data, and everything that you need. So the basic definition is like you are roughly building a model that learns itself to select the sample that it needs to optimize its own performance. Oh, sorry. So usually the whole active learning loop looks like that, where first of all have your model that you are training. You start with a like small amount of data, and what happens is like you have an acquisition function that allows you to make the selection in batches. And as you do that, roughly, it is the stage where your model is trying to know or to point finger at samples in the data space that it needs to maximize its own performance. And obviously, like if you are in a labeling setup, then you can use that to actually know which samples to label to allow faster convergence and better optimization. So, there have been many benefits to this because many papers have shown that you can, like using active learning, you can achieve like high performance with only more or less 20% of like labeled data. But the performance that you achieve is still like highly competitive, as opposed to other approaches that, for instance, needs lots of data, especially now that we're in the era of LLMs and everybody's like trying to run for the scaling laws and like just exploding on compute and everything. So we are going to, sorry, I'm going to move next. So I'm going to walk you through a few series of paper that talked about this and like shows how this can be efficient in like practical like uses. So the first one is like active learning for speech recognition. Roughly the idea here is like you need to have a model that allows you to transcribe, right? But the interesting question is like, if we're in the low resource settings, how can we prioritize which samples to like select from? So this paper was published last year at ACL, and the idea was like, how can we build, the problem at hand was like, how can we build African accented English speech recognition systems? Like, I assume like we all speak English, but the way I speak English is not like the way a native speaker will speak English. It's not the same way like South African will speak English. It's not the same way Nigerian will speak English. So the accent is like pretty much important to not butcher like what is being transcribed. So in this paper, I wanted to show that we can use active learning to have more efficient systems, but at a way better efficiency cost. So roughly, wait, I will try to, I will try not to go too deep into techniques, but this is roughly like the different steps that everything goes. And what is interesting here is that we can make, using like acquisition function and like guided by the principle of like the epistemic uncertainty, we can adapt the learning of each accent by our own model. It's still one model for everything, but you know we have different, I'll say, way of like learning representation from each subset of like accent. And obviously, this is like the standard way of doing the active learning loop, and we always want to query from a data set that we call like the pool data set. That is like a technical term, but you can assume that is a pool from where you want to know which samples to label from. And roughly, this is like the whole process, and I'm going to now move to the result. So like the baseline here is like roughly when you take, for instance, wave to vec, and you throw 100% of your data set. Like you have a bunch of audios and transcriptions. We have three different approaches. So this is the baseline, like the normal way that people do the like ASR. And when using the active learning approach, we can see that the performance jumps from like 21 order of rate to 15. This is almost like 27% of improvement across like the general domain. And here we have the clinical setting where, like you can imagine, for instance, in a setting where like they are talking with patients, like doctors, like having conversation with patients and things like that. And when we combine both domains, we still have a way better performance using like the active learning approach as opposed to when we just feed 100% of the data. So roughly, it's how it showed that we can outperform the baselines in each of those like domains by using 40% less of data, and that implies that you are using like less compute. Now, moving on, what is actually interesting, because the whole idea of active learning is like you need to be, like as you are exploring and exploiting your data space, you need to be able to see that the variance is reducing, because the epistemic uncertainty is basically because your model doesn't know. So it needs to be able to know what it doesn't know, but then as you are progressing through the rounds, it needs to acquire like more knowledge. So what happened is like, if we are now across the clinical domain, what we can start from here.
Just for people online.
Oh, okay. We can start from here. So from the general domain, like you can see that the epistemic, the uncertainty, like the variance of the model, like the quote unquote, the variance of the model with respect to each accent, these are the top, like most uncertain accent across the whole data set. We can see that across the rounds, it decreases. So that means that our model is like getting more and more adapted to grasp better those like different accents. And we have the same thing, same scenario across like the clinical domain, but I mean on the last round, like it got exploded, which is why there's always needs like to have like a threshold to know how many rounds you actually need to run. And we also have the same scenario across like the top, like when we combine both domains. So that is just one example in like the speech domain that can show that we can have better AI system by like exploiting the constraints, for instance, that we have to build things that are more contextualized to the African context, and by also saving resources. And I won't make names, but this has already been like used like in real life, like startups and things like that. I'll move now to the next point. That's just the summary because I don't have time. I'll move to the next point. But the next things now, because everybody's talking about LLMs, this is a work that was published actually 3 years ago at NLP that tries to use the same approach, but for language modeling, multilingual language modeling. So we call the word AfroLM because if you remember in the beginning, there was this part which was important. But because we were pre-training from scratch, and we didn't have like all the, like, I would say our model haven't been seen on like all the different languages. This part was omitted, those two parts were omitted, and the whole thing was done by the model itself. That's why we have the self, because it's like reflecting on itself. So quickly, how it happened is like we have these like data set of like n languages that we split into two data sets. Then we have the normal active learning round, and we have this part where we take the header data set to generate new sentences that ideally for the language follows the same distribution, the token distribution. And we validate them by, for instance, computing the word error rate between the target and between what has been generated. And given the threshold, those new sentences are added to the batch, and then we restart the whole process. Basically, like roughly as I described a little bit earlier. So we have a lot of experiment, for instance, on like many African data sets. And what happened is like, we can see here that our approach obtained the best performance despite being trained only on like a small amount of data sets, as opposed to mBERT and XLMR, which were trained on like terabytes of data set and probably for like many months of training. We still have the best performance in average across all the languages. Now, when we move to out of domain, I mean, those are other like benchmark that we evaluated on. When we move to out of domain, what happened is like we can still see that our approach still works better than like other existing approaches. And then, yeah, we still have the same result here. So even in the language modeling setup, where the idea, the common idea now is like just to take a vast amount of data and then just to throw and then like to pre-train the model, we can still like use active learning and have even a better, more efficient and effective way of doing like creating like more Afrocentric LLMs. Now, this has been done, but then another interesting thing like that I tackled recently was the fact that when like across all those works, and generally what happened is like we have, for instance, a data collection stage, and then like we hire annotators, but at the end of the day, we do not really track the progress. What happens is like we take the data set at the end, and we just like fine tune or like pre-train whatsoever on the downstream task. So this task was actually trying to combine active learning with a combinatorial like approach for this situation where like you can imagine you have, let me say 10,000, and you want to create to label a data set. Which sample should you label such that you not only optimize, like you do not overspend over your budget, but you also optimize the performance of your model when you like, for instance, like throw the data at it. So it was recently accepted at EACL this year, and like it's going to be presented, I think is in Morocco. So we called it like active learning for non-uniform cost for African language processing. So the main idea is like we want to create like, to incorporate the constraints. So here the constraints are just like the budget that we make available to take to have the whole model and the data set built. So we want to make sure that we incorporate those costs to optimize resource allocation, but at the same time by maximizing the performance, because that's what we don't want to sacrifice. So we quote unquote combine like an informativeness-based selection method, and we combine also like a combinatorial like optimization technique. So the knapsack problem is actually an NP hard problem. So we try to use this to obtain knapsackBALD, which optimally in real life can optimize data labeling by showing which sample or sentence you should label first, so that on your downstream application you have the maximum performance. I'm not sure if I have a lot of time, so I'm gonna skip through this, but it's like basically like the whole math around how we like create data set, the unlabeled data set that we have, which is supposedly like the sample, the set of like samples that you want to label. We have a cost function that allows you, depending on your scenarios, to know which samples to, not to select, but like how to attribute a normal cost for it. And we have a global budget that you should abide by, and then we have like bunch of like batch acquisition functions. Now, what happened is like, since we are now trying to use the knapsack approach, roughly the knapsack is, let me assume that you have like 100,000 and you go to the supermarket, but you have a bag of like, that can maximum contain 1 kilos. So the knapsack is how can you select the items from your supermarket such that you stay within your budget of like 100,000, but by staying also, by abiding by the requirement of your bag, which only can contain like 1 kilo of like product. And so that is roughly we are maximizing, because we still want to make sure that while we are we are staying under the constraint of like the cost, we have the selection of like samples that are informative for the model, for the downstream task. So I think like we have like 2 different methods. I'm going to skip through. And roughly what happened is like we have the performances here. So the baseline is like the normal way people do like the whole process, like using the active learning approach. And we have those 2 techniques as our approach. And what happened is like we can see that we get way better performance. Now we created different scenarios in which it depends how the annotation is done. So for instance, this scenario 2 depends on like the annotator's like reliability. So we assume that if you are asking someone to label a sample, if the person has more experience like in the labeling, then the more experience that person has, the higher it should be paid. And same thing for the level of extremity, for the scenario 3, where it depends on the sample difficulty. Like if the sample that you are labeling is difficult to understand, what happens is like we assume that you should be paying more the person who should focus on it, as opposed to like something that can be quickly and easily understood. Now you probably noticed this level 1, level 2, level 3. I can go back here about how we created those different like functions. 1 second. No, it's not here. So roughly, if I can come back to this space, roughly what happens here is that we have, depending on the scenario, we know how we sample the different costs. But you can imagine a case where there are a few, like if you have a budget of 5,000, a few, let's say 100 or maybe 1,000, take up to 95% of the whole budget. And everything else is like split among what is remaining. So in that scenario, how the model should still be able to allocate where the resources while maximizing the information like that is given to your model. And this is what we have. And what it shows is like as we are moving deeper and deeper and having more extremity, our performance of our method is getting wider and wider across different scenarios, across different language, across different like levels, and still is beating the baseline, which if you can see the progression has been like decreasing. And we wanted to see if there's like quote unquote like I wouldn't say correlation, but if there's like a relationship between the cost extremity and the whole thing. So I will quickly wrap up by, okay, so this is another paper, but I wouldn't have time to present. And the last thing I wanted to quickly talk about was something that I'm currently working on, like just 1 or 2 minutes. The way we currently do evaluation is pretty bad because we just like select a data set and then we have a metric, downstream task metric, and then we perform the evaluation, we take the average. But I think it's pretty wrong because it doesn't really allow us to know the underlying understanding of the model on the task. So what happens is like, we know that evaluation is expensive, not all questions are equally informative, and a standard benchmark treats them as uniform. But then the problem is, how can we make it better? So what I have as an idea is, I'm not sure if you guys are familiar with item response theory, but the whole approach is like, instead of like throwing the data at your model, you want actually to have an estimation of how difficult the sample is and how discriminative the sample is. So then if you have a population of LLMs, for instance, or system that answers the question, what happens is like you can rank them to know which one will be able to answer this question, which one will be able to answer these harder questions. That will allow us to have what I was calling a model skill, right? And roughly, like, we will have an evaluation that is going to separate the model, shrink the uncertainty, and that evaluator roughly is going to allow you to really understand if your model knows your task. And if the model really knows your task, so it should be able, for us, as opposed to IRT phenomena like that are normally asking what is the probability of a model answers a given question correctly. What happens here is that we will now be accounting explicitly for like the variations, the model difficulty and the item difficulty. And I'm going to quickly show the result and move. So we now train like the skill as latent variables that can be learned actually, instead of like something that we just rely on from the benchmarks. And we have some like preliminary results. I'm not really yeah. So if we can see here what happens, like we have the models, we have the skill estimates, we have the variance. And one thing that is interesting is like, I think if this works, that will mean that you can be able to estimate how well your model will perform on a data set by knowing the model, the level of the skill level of the model. So instead of like evaluating 100 or a huge amount of data sets, by knowing the skill of your model, for instance, you can infer how well it will do, assuming that your model answers correctly like most questions. And that could be a very good shift like in how we do evaluation and also how fast it happens. Yeah, so I think that is it. And like, sorry, like we had technical issues, but that is what I wanted to share with you roughly today. And I know like AL is not something most people work on. It's mostly used for drug discovery and everything, but I hope I was able to show you quickly, even though I skipped through some slide there. This is one of the ways we can go about to build more efficient like system for low resource settings by taking into consideration constraints from the environment, data, compute, and everything else, and also like from an evaluation perspective. So yeah, thank you.
Thank you, Bonaventure. Does anyone have any question? If not, I have, yeah, there you go.
Thank you, Bonaventure, for your talk. I want to come back on the talk where you speak about the cost, the pack. And my question is, how do you construct the cost that you allocate to each data sample?
Good. So that is a good question because in practice we didn't have it. So that's why we like simulated it. So for instance, we have a scenario where we, for instance, simulate like the annotator's reliability. And now using that annotator reliability, we pass it, for instance, to a monotonic like function, like an exponential functions that allows you to have like higher cost for higher reliability and lower cost for lower reliability. Now, that being said, if now you have the cost, the real cost, you can just plug it in and everything else like will just work out, and you should be able to have like a table like this.
Okay. Okay. So that brings me to another point.
Okay.
I mean, I got the opportunity to be exposed a lot to the cost-sensitive learning literature. And recently, people, as we don't have by default the right cost, people start to imposing a kind of uncertainty measure on the cost.
Yes.
To, I mean, improve the reliability of the system. Do you think that we can, I mean, shift a bit what you did here and trying to take also account the uncertainty on the cost, which is construct using the segment?
Yeah, I think what you are talking about might be presented somewhere here.
Okay.
Because if it's about the uncertainty from the model, we are getting that here. That is this metric. So we are like So for instance, here we are using BatchBALD, which actually tries to maximize the mutual information between your model's parameters and your model's predictions. Now, if you want to use a purely uncertainty based approach, you can still, but then that will mean, for instance, that you might want to minimize, because what your model is most uncertain about is, like, for instance, what should maybe cost more to label, for instance. But at the end, it should be able to be helpful for the learning of the model to improve the performance.
Okay,
So those are like ways like you can play around this.
great. Okay, great. My latest question about the skill.
Okay.
Do you see the application of the skill, concept that you introduced here in, for example, the medical imaging settings and
Okay. So in the medical setting, let's say, honestly, I don't know. In the medical setting, honestly, I don't know. And this is like still under running, because another things that I'm trying to run is trying to have different other metrics. Like, for instance, if a model does well on a benchmark, for instance, let's say, for instance, a mathematical reasoning task. If it does well, for instance, on GSM 8K, can that skill be transferred to another like mathematical reasoning task? So far, it's been doing well, but not better, like on par with like the baselines. But I'm still running the experiment, and then it should definitely be better. But then, like, it can be very useful for many other contests. Okay.
Yeah. Thanks for your presentation. I wanted to clarify something. So you said that if you have several, let's say LLMs, for instance, you can rank the one that would be the best to answer a given question.
Yes.
So how does it play in your optimization scenario? Yeah.
Good. So what happens is here, like, is like I took the idea of the inspiration from like the item response theory. So what happens here is, like, you can assume that you have, let's say, like, we have this classroom, right? So we have a list of questions, and then we have a list of subjects. So you, me, her, him, everybody answers the question. So now, using that population, we can have an estimation of like how a specific question is difficult and how discriminative a specific question is. So if we have that estimation, we can allow us, like each other, to label, like, for instance, if you're able to answer most easier questions, that means like your skill is pretty much lower